Hi everybody, today we're going to be doing a video of scientific notation in the metric system. So for your notebook you can set it up like this. We're going to take notes on the right, KCQ boxes. The little slip you can print from the website will be some practice problems and some little diagrams for you, and the worksheet will go on the left side of your notebook. So first, I think it's kind of fun to just look at some times where conversions and measurements caused some problems. You can kind of see why it's important to be using the metric system. So first, in 1999, NASA lost a Mars orbiter, which was a $125 million piece of equipment that got lost. They did a calculation with pound force seconds, not something called Newton seconds, which caused everything about their calculations to be wrong and cost them a lot of money. This one's kind of scary. In 1983, a Canadian plane accidentally ran out of fuel in the middle of their flight. They thought the fuel was put into the airplane and was weighed in kilograms, but it turned out it was weighed in pounds. And so they didn't have enough fuel. They had a little less than half of what they needed to. Luckily, they were able to land and nobody was hurt, but that's kind of scary. 1492, Columbus ended up in the Bahamas instead of Asia where he thought he was going. And what they now think is that the reason he ended up off track was because everything was being measured in Roman miles and not in nautical miles. So that got them off course. 2004, in Tokyo Disneyland, the Space Mountain ride had an accident. They changed the designs and they ended up using metric instead of inches. And then that caused one of the pieces on the ride, an axle, to be too thin. And it was weaker than it should have been, and the whole thing derailed in the middle of the ride. This one's kind of fun. In 2001, the LA Zoo loaned a giant tortoise named Clarence to another zoo, and they kept telling the other zoo, "Are you sure you know how big this guy is? He's really, really, really huge. He weighs 250. And the zoo they were loaning him to thought they meant 250 pounds, but it was actually 250 kilograms. So their fence wasn't strong enough, and they had to reinforce it, because 250 kilograms is a lot bigger than 250 pounds. It's a really giant tortoise. So a couple of reasons why we need the metric system is so that everybody's using the same language. We want to make sure that all of our math is going to match each other. We have the same math language. Everybody else uses it. There's only about 2 or 3 countries that use something other than the metric system. We are one of them. So it's, the more common one is the metric system. And once you get used to it, it's actually easier. It doesn't feel easier in the beginning because we're not used to it. But once you see how it works, it actually makes our lives much easier. We can do our work much faster using the metric system. So how is it easier? Metric system uses something called base 10, which means that everything is going to change by a factor of 10. So instead of using completely random units, we'll be using these nice increments of 10. We either multiply by 10, multiply by 100, multiply by 1,000, or we divide by 10, divide by 100, divide by 1,000, etc. So you can see here some of these English system ones that are just completely random. You'd have to memorize them all or use a chart. With the metric system, there's very little to memorize, and all we're going to have to do is move our decimal points around. So we don't want to be using those, not very helpful. Let's use the metric system. So this is on your little glue-in paper. This is the metric staircase. So it's a way of organizing some of the prefixes that we're going to use. We're going to use kilo, hecto, deca, base unit, deci, centi, and milli. And so there's ones that are above this, there's ones that are below this. These are the ones that you'll have to memorize. You will need to know this section of the staircase. And what we'll be doing is we'll either be multiplying to get to a different one, or we'll be dividing to get to a different one. We'll either be going up or down the staircase, left or right. And it just requires us to move our decimal. So base units, if you see here, kind of the middle of our staircase, we call the base. Base units are the ones that we just kind of consider as standard that don't have a prefix on them. So when we talk about a base unit, we're going to talk about the ones that have no prefixes. So instead of kilometer, it's just a meter. Instead of milliliter, it's just a liter. So anything right in the middle of our staircase is our starting place. A good way to remember the prefixes is this weird little mnemonic. This is the one that I learned when I was back in high school. There's lots of them out there. You can learn whichever one you want, whatever helps you remember them. So I always learned King Henry died by drinking chocolate milk. Kilo, hecto, deca, base unit, deci, centi, milli. Remember, base is the one with no prefix. These prefixes you would add on to tell people how you've altered your base unit. Be careful with deca and deci because deca is a capital D, deci will be a lowercase d. You can also spell deca with a C. I've seen both C and K, they're both correct. So let's do some practice. We're going to go from milligrams to grams. So step 1, are we going up or down the ladder? So what I like to do is I like to literally list out the prefixes. King Henry died by drinking chocolate milk. I put a little dot where I'm starting at milligrams. And I'm trying to get to base unit because grams up here has no prefix. Because it has no prefix, it means it's a base unit. Then I'm going to see, okay, I'm going to the left. How many steps to get there? It's going to take me 1, 2, 3 times of moving my decimal. I'm going to move my decimal to the left. 1, 2, 3. That's the same as dividing by 10 3 different times. And I get my final answer with my new unit. The next one, if this up here is a capital D, that makes this deca, right? Or you could use the K, it doesn't matter. But we've got to make sure that we capitalize that D. So we're going to start here. We're going to end at milliliters. I'm going to the right this time. 1, 2, 3, 4 times. I'm going to move my decimal 1, 2, 3, 4 times to the right. My number looks bigger now because milliliters are very small. There's going to be a lot of milliliters in a deciliter. So there's 1,500 milliliters inside my 0.15 deciliter. In chemistry, we get some really big and really small numbers, so it's nice to use scientific notation. It'll allow us to move our decimal and rewrite it in a format that takes up less space. We're not likely to miscount how many zeros there are. It's a little bit safer. This is also on your glue-in paper. So we're going to put one number, then we put a decimal, we put any other numbers there are, we multiply it, and because metric system and the way we do things in science is base 10, we're going to multiply it by 10 and raise that to an exponent. That exponent is going to tell us how many times to move our decimal, and do we move it to the right or do we move it to the left? If our exponent is a positive number, we're going to get a big number multiplying it by tens. If it's a negative number, it will be small and we'll be dividing by tens. Realize big and small is relative to where you start. You could say it's just getting bigger or it's getting smaller. The measurement itself is the same, but your number will look bigger or look smaller because you're just changing the format. Also, when you're gluing, a couple more guided practice problems. Make sure you are doing these in your notebook. That is part of the notes. It's not optional. So let's do the first one. I want to take this and turn this into standard notation. If I'm multiplying by 10 to a positive number, I'm going to be making my decimal move to the right. I'm multiplying by 10. So multiply by 10, move one time over, and my answer ends up 10. Scientific format, standard format. For the next one, 10 to the 0 is the same as multiplying by 1. Anything to a 0 power, so I don't even have to move my decimal. It's just going to be 1.0. Now this one is a negative exponent. I'm going to move my decimal one time, but this time I'm dividing. I'm not going to move to the right, I'm going to move to the left. So now our number has the decimal there. And we want to make sure we never leave a decimal kind of hanging out by itself here, right? Make sure you put your 0 in front. We don't want to have kind of sloppy notation. For the next one, it's to the 4th power, so it's 2.5. I'm going to multiply by 10 4 times, which means I move my decimal 4 times. Oops. 1, 2, 3, 4. I like to kind of put dots or little lines trying to make sure I count correctly. So I should end up with 2, 5, and then 0, 0, 0, and my decimal is at the end. So my final answer is 25,000. I tend not to put commas because sometimes I feel like people write little teeny tiny commas that look like decimals and it can be a little confusing. But if that's helpful to you, go ahead and put commas. Just make sure that you're making them very clearly a comma and not a decimal. Right, next one we're going to have a -2 exponent. So I'm going to be moving to the left. And some technical problems. There we go. 1, 2. So I'm going to have 0.038. You see that I didn't leave my decimal hanging out by itself. I made sure there's a 0 in front. All right. So we have all of our final answers. All right, let's do some going the other direction. So now we have standard notation and we want to put it into scientific notation. So the way we're going to do this is we're going to see how many times and which direction do we have to move the decimal so that we get one number in front. And then our decimal, and then the rest of the numbers. So 5, 4, 1. I need to get my decimal to here. This is the goal. So right now it's starting at the end, and I'm going to need to go 1, 2 times to the left. So 5.41 times 10. And then the question is it positive 2 or negative 2? Well, if I put a positive 2, that's going to make 5.41 times 10 times 10. It'll match my 541. If this was a negative 2, I'd be going the opposite direction. I'd be going further away from my answer. So my final answer should be 5.41 times 10 to the 2. All right, let's do the next one, 9.5. 9.5. Now, if I look at this, I already have one number and then the decimal. So I don't need to alter this number. But if I wanted to write it in scientific notation, I still need it to be times 10 raised to a power. The only exponent I can put up here that wouldn't actually alter this number would be a 0. That's the same as multiplying by 1. So it would leave me with 9.5 times 1, which is clearly the same as 9.5. So my final answer is 9.5 times 10 raised to the 0 power. Last one, 0.025. In order to get one number and then my decimal, I'm going to have to go 1, 2 times, but this time I'm going to the right. So it's going to be 2.5 times 10, but it's not a positive 2, it's a negative 2. If I wanted to go the other way, the negative would tell me that I need to go 1, 2 to the left so that these match each other. So 2.5 times 10 to the minus 2. There we go. I hope that video was helpful. Bye, everybody.